All right. Let's get started on, uh, I guess, where we left off, which is sort of a review of the things we've been doing recently for feature selection. So we started this unit considering plain least squares without any feature selection on this PSA dataset. And because of the bias variance trade-off, when we use all our features, that means our bias is low, but our variance is too high. And for that reason, using all the features doesn't do very well. We can see here um, the cross-validation mean squared error is this number here, 0.403. And then we said, when we started talking about feature selection, the first thing we talked about was exhaustive search least squares. So for this, we look at every possible combination of features. For each one, we do cross-validation mean squared error to see which one works best, and we just choose that particular subset of features. This is the best performance, in this case, 0.388. Another technique we described was sequential feature selection. This one, even though it's not optimal in general, works pretty well. And in fact, it gives us the same performance as the optimal, at least, for this experiment, this seed for the cross-validation mean squared error, shuffling, and so on. We also talked about recursive feature elimination using mutual information. We said that's not usually the best approach. And here we can see that, in fact, it is not doing as well as sequential feature selection or the optimal technique. Then we moved on to talk about regularized methods. We first described ridge regression, where we add an L2 loss onto the RSS, and we have to do some tuning of the alpha parameter for the L2 loss. We do that with cross-validation. And what we find here is that the performance is not great. And this is, as we know, because ridge biases our coefficients towards zero, so they shrink. And also it does not perform feature selection. It does not turn off any features by setting the beta coefficients to zero. So the reason that we usually want to use ridge, if we use it, is because it's really good at handling feature correlation. So the fact that ridge is not performing that well on this data set is an indication that feature correlation is not really that big of an issue with this data set. So overall, ridge is not performing very well. A little bit better than plain least squares, but not very well. So the last thing we discussed was lasso, where we take RSS and we add an L1 loss. And so this method does drive certain subsets of coefficients exactly to zero. So it does do feature selection, but it also has this issue like ridge, where it shrinks the remaining beta coefficients towards zero, and that induces bias. So it does a sort of navigation of the bias variance trade-off. Variance decreases when you turn off coefficients, but the bias will increase if you shrink the remaining coefficients. So as a result, plain lasso on this problem actually does, really pretty bad. It's worse than all methods except for plain least squares that we've seen so far. So then we said there's smarter things we can do. For example, we could run lasso first, figure out which features it wants to throw away. And then on the remaining features, we can just fit linear regression, least squares linear regression. And that's what I'm referring to here when we say de-biased lasso. So de-biased lasso, here we are. De-biased lasso definitely improves the performance over biased lasso, but still, this is not very good. And the reason that this version of de-biased lasso is not working very well is because when we did the tuning of the alpha parameter, we were tuning so that the performance of the biased or plain lasso is best. And that's not actually what we care about. We want to tune the alpha parameter so that the result of lasso feature selection followed by least squares linear regression, so that that performance is best. So then we describe two different ways to do that. One of them used a for loop, and one of them used the what's called a pipe in scikit-learn together with grid search cross-validation. Both of these methods are performing equally well, and you can see they're performing significantly better than these other lassos. And in fact, they're performing almost as good as exhaustive search least squares. So that's sort of a summary of what we have. Something to keep in mind here is that these numbers will change if you run things again with a different seed when you use the seed that's used for the shuffling in k-fold cross-validation. So yeah, this is just one experiment, but the trends here are what we would expect to see. Okay, so the last part of this unit, very important part, is coming back to some statistical interpretations of what we have been doing from the beginning of the semester. So essentially what we're talking about now is estimation of statistical parameters as a framework to understand machine learning. So according to this framework, you come up with some probabilistic model of your data. And we'll see some examples going forward. And given that probabilistic model, you apply some well-known estimation techniques, as we'll describe maximum likelihood and maximum posteriority, or MAP. And if you sort of do this procedure, declare a probabilistic model, and use one of these approaches, you can find that you kind of recover what we've been doing all semester, but you then have a justification. It's not just like some kind of heuristic least squares technique. You actually understand when and why that might be a good thing to do. So that's what we'll learn next, and we'll see connections to least squares, ridge, and lasso from this point of view. And this is going to be the main way going forward in the semester that we are going to tackle new problems. In particular, we're going to move from regression to classification in the next unit, and this will be the way that we will derive our predictors for classification. So let's just start at the beginning. Let's say that capital Y is a random variable that depends on some unknown statistical parameters theta. So that's what we're saying is going to be the probabilistic model. To be a little bit more detailed about this, as we described a couple lectures back, Y is fully described by its probability density function that we call this Py, probability density of that random variable Y, given the parameters theta. So I'm writing that in this case with this dot here. We could, if we, for example, put a little Y there, then this quantity would mean the density evaluated at that particular Y. Without putting that particular Y there, I'm just saying this is the density as a function. And for that function, you can put in any possibility of capital Y, and that would measure the density at that value of little y. Anyway, so this is what we have. The PDF is what we're going to be working with. And in terms of visualizing the PDFs or even like writing down an equation, we often think of it as this function, the density of some particular y given some particular theta. We often think of that as a plot versus y, or a function versus y. And in doing so, we're sort of implicitly saying for some hypothesized values of the parameter theta. So let me just give you a concrete example. So let's suppose that I have a random variable that is Gaussian. And as we know, a Gaussian is parameterized by two numbers. This is just a scalar Gaussian. So we're going to have the mean and the variance. And in practice, we might say, okay, I have this Gaussian. I know that there's some mean and variance that characterizes it, but I don't know what those things are. And so that would be the theta. In this case, theta would be the vector this vector theta would be the vector of those two unknown parameters, mu and sigma squared. And finally, the probability density for a particular y, given my parameters theta, would then take this form. So this is a very kind of famous equation. It's going to pop up a lot going forward. It's a sort of a good thing to memorize if you, because you'll be using it a lot. So essentially what we have is we have an exponential minus 1/2 times the variance, and then we see y minus its mean squared. So that's sort of describing what's important about the data. This part is giving us a scale factor so that when you integrate this over y, the integral equals 1. Basically, this part is sort of showing the shape of the curve, and this gives us this bell curve. So the largest that the argument to the exponent can be, that happens when y equals mu. And when y equals mu, this whole thing goes to 0, and that means that this thing, e exponential of 0, is 1. So, so that sort of tells you where the peak is. And then as y deviates either greater or less than mu, it's this sort of symmetric thing where it comes down. And because there's an exponential here, as this quantity starts to get more and more negative, the exponential vanishes very quickly. So these tails go down very, very sharply. And this is our bell curve that I'm sure you've seen in other classes. And so basically, yeah, we have the mu is the center of the bell curve, and then sigma squared, the variance. If you take the square root and you get standard deviation sigma, that tells you the width of the bell curve. Okay, so that's sort of just how we often think of these PDFs. We think of it as a function versus y. But it turns out that when we start to do this parameter estimation of theta, y is actually data, training data that we've been giving. So it doesn't really make sense at that point to think about this as a function of y. In fact, at that point, we really want to think about this as having fixed y, but unknown theta. So this would be a function of theta. So let me just show you a little bit more of that in detail. So of course, in practice, we're not going to have just one data point. So in this equation, we just have a single scalar y, but that's not what happens when we train. When we train, we have samples y1 through yn. So we can create a column vector from that, call it boldface y. And so these are independent samples of some random variable capital Y with some PDF. One way we think of these y's, each individually, we can think of those yi's as a realization of a random variable capital Yi. And so at that point, we would have n of those random variables. But we can also say that these random variables are basically copies of this sort of y without a subscript. So these are just sort of equivalent ways of looking at it. We can think of these numbers as independent realizations of this capital Y, or we can say, I take the capital Y, I sort of copy it and make all these capital Yi's, and then Y1 is a realization of capital Y1, Y2 is a realization of capital Y2, and so on. Okay, so we're going to focus on this random yi case. And so essentially what we're saying now is we have these n random variables, capital Yi. We're going to assume, when we do ML, that these are independent, statistically independent random variables. And here we're saying they're all distributed exactly the same. That means identically distributed. Together, those things are called IID, independent and identically distributed. So in this case, what we have, just one moment. So what we have is, because of this independence, we know that the joint probability or joint density over these n different random variables is the same as the product of the density with respect to the first times the density with respect to the second, and so on. And we can represent that product using this big pi notation. This is a product over the index I going from 1 to n. And now we're going to have the probability of capital Yi. And this is going to be evaluated at little yi as a member of this vector y. And this is the same distribution given our hypothesized theta vector. And if we want, we can also think about this. So that's what you get out of the independence. And what you get out of the identical distributed is that since all the yi's are statistically the same as y, you could also write this as p capital Y of yi given theta. Okay, and now we have this function here. This is called the likelihood function. But I want to emphasize that when we talk about the likelihood function, we treat these as fixed because they're our training data. And we think about this theta vector as something that's variable, something that we like to know what happens under different hypotheses of theta. So that's something I really just want to emphasize, because traditionally when we think of these densities, we tend to think of the conditioning variable as fixed and this other variable as, here we're varying it. But really, when we do maximum likelihood estimation, what we want to do is think of the yi's as fixed, and we want to think of this function as a function of theta. Okay, so now finally, the way that we predict or guess or estimate theta in this maximum likelihood framework is we simply say, find the value of theta that maximizes this likelihood, py given theta. So here, this one is an abbreviation for this. So in this abbreviation, I just didn't write this down here, but it's the same thing. Okay, so this is the maximum likelihood idea right here. This is how we're going to find our parameters. So again, it's now going to be a matter of choosing our assumption, in particular our assumption on this, and then somehow doing this maximization here. In some cases, this maximization is something we can do analytically with pen and paper. In other cases, it's something that maybe we have to run an algorithm to do. We'll see some examples of that going forward. Anyway, so this is our maximum likelihood estimate. And the form of this, as stated here, is a little bit inconvenient because we're trying to maximize theta over a product of different things. And there's an easier way to formulate this, which is to, instead of maximizing this likelihood, we can maximize the log likelihood instead, because the log likelihood is equivalent from the perspective of maximization. So we have argmax of the log of P, Y given theta. So that's because when you have the log function, so this is, let's say, log of, yeah, this is just, maybe I'll just do X. Not X, I'll use Z. Okay, so here we have log of Z as a function of Z. This curve is monotonically increasing. So that means if if I have a list of hypotheses, the one that maximizes Z is also the one that maximizes log Z. So that's why it's equivalent. You can do this maximization or this one. They're the same thing. And one final thing that often makes the equations a little bit more elegant is instead of maximizing the positive log, you minimize the negative log. Arg min theta of negative log like that. So, so in practice, this is usually the one we use. Doing that is equivalent to doing this over here. Let me highlight this one. So we'll see some examples of why we want to do this one over here. Okay. And the difference between this maximum likelihood estimation and the thing we'll cover in a few slides map is that in doing so, we are not making any assumptions about this theta vector. We're not saying something like, well, I think some thetas are more probable than others. Let's bring that into things here. No, we're making no assumptions about theta, just saying essentially what I want to do is maximize this probability y given theta. Okay, so let's do an example of this, see how it works. And we're going to consider linear regression, same thing we were considering in Unit 2. And essentially, the question now is, what if we try to apply this idea to fitting the parameters beta in linear regression? So in this case, beta would be our theta. So here is sort of like, you can do this with a generic theta, and now we're saying, let's look at linear regression where theta equals beta. And furthermore, let's make this assumption. Let's assume that we have so-called linear Gaussian model, which takes this form. So here, we've seen actually a very similar equation before, but here is our y equals, targets equal features times prediction coefficients plus noise. So we've definitely seen this. We saw earlier a version of it that said this, y is approximately equal to x beta. We're being a little bit vague about, about that approximation. We have also seen this equation here back in Unit 2 where we called this the residual error, prediction error. But now we're going one step further. I'll highlight it in a different color. We're going one step further and saying those errors are zero mean variance sigma squared Gaussian. And across all the different entries in our training sets, those errors are statistically independent. Okay, so this is the new part. We've never made this assumption before. But if we have this assumption, that is what defines our probabilistic model. Because essentially, remember, our features, this is just data we've collected. This is something, it's just given to us, same with y. Beta are the parameters we're trying to find. So there's no randomness here. The random part really, the part we don't know is the epsilon vector. And this is our probabilistic model that ties everything together. Okay, just another quick comment. I think earlier we saw this with the A matrix, and that's what you want if you're using an intercept term. But we're going to assume that beta 0 equals 0 because we standardize the data. And so in this case, our beta vector starts with beta 1 and goes up to beta d. Okay, so so in this case, if we want to look at what happens for the ith target yi, we are going to have the equation xi transpose, that would be the ith row of the feature matrix, times the beta vector plus epsilon I. And so if this is our, if this is our model for yi, and we'd like to figure out from this, how do we get this model here? We have to think about it this way. In this model, we're conditioning on x, meaning we're treating x as fixed. We're conditioning on beta, treating beta as fixed. So these are just fixed numbers, not random. This is the random part here. And we're saying that this variable y essentially is zero mean, Gaussian noise plus a fixed offset. So if I take that zero mean Gaussian noise and I add a fixed offset, that just means that the mean of the sum is no longer 0, but it's actually this. So finally, putting this all together, the density is a Gaussian, where the variable of the density is yi. The mean, mu, is xi transpose beta. This is the mean. And the variance has not changed. It's still sigma squared, because all I did is I shifted this epsilon by a fixed quantity. I did not change how much epsilon varies. Okay, so this is sort of a key step in these problems, is being able to start with some equation like this, and then from that figure out what is the density we're talking about. So this is the density that we have for this linear Gaussian model. Okay, so now we're ready to go through just a few equations here. This is the thing that we said we want to maximize. This is sort of a generic expression. Now we're saying, let's also think about these features in here as just some deterministic numbers, deterministic in the sense that we're conditioning on them, so we're treating them as deterministic. And because of this independence assumption, just like on the previous page, this joint conditional PDF can be written as a product of the individual conditional PDFs. And so that's product over the different training samples I. We have this. We know that this is given by this equation over here. And so this Gaussian, that equation we've seen over here. So if you have a Gaussian, mu, mean mu, variance sigma squared, it takes this form, where you can see where you find the mu and the sigma squared. So basically, applying that equation down here, here's our mean. And here's our variance that is reflected here and here. So this is, we have a product of these things. So this would make, yeah, okay, so let's go a little further. So if I have a product of these, and there's a product over n of these, I can move this out of the product if I take this to the nth power. Taking that to the nth power gives us this term. Then I have a product of these exponentials. But remember that if I have a product of exponentials, just as for example, if I have exponential a times exponential b, this equals exponential of a plus b. So when you have a product of exponentials, that is the same thing as having exponential of their sum. So essentially this product outside the exponent can move inside the exponent here, but when turning into a sum. Okay, and the very last step is to realize that this sum of squares is actually a Euclidean norm squared. And so we're just writing that finally as this Euclidean norm squared. Okay, so this is our likelihood over here. I'm going to highlight it. So this is our likelihood. And the maximum likelihood estimate is the values of beta that maximize this. Or we said we can also equivalently, we don't want to look at the maximizer, we could look at the minimizer of the negative log likelihood. So let's apply that idea. So if I take the negative log likelihood of this, right, what happens is I take the log, the negative log, the numerator, the log will cancel the e, the negative will cancel this minus sign, and what we get is this. And then we're going to have minus log of the denominator. But if we're maximizing or minimizing over beta, this is just a scale factor that's not going to affect us at all. So essentially, at the end of the day, we're interested in maximizing, or in this case, minimizing this quantity. So finally, this scaling of it also doesn't affect the minimum, because we're saying what is, what are it affects the minimum, not the minimizer. So since we're looking at the minimizer, we essentially have can look at arg min theta of y minus x theta norm squared. So at the end of the day, the ML estimate for this linear regression problem with this, oops, sorry about that. For this linear regression problem with this particular Gaussian noise model is exactly our least squares problem. So if you think back to Unit 2, we really had no justification for doing least squares, except for saying that it was a simple thing to do. It's like a familiar thing to do. Now, from this perspective of maximum likelihood with this particular assumption of Gaussian noise, this has a better justification. This is sort of a principled thing from statistics that you want to use. We're not going to get into all the statistical properties of maximum likelihood estimation in this course, but it's one of the most famous methods and essentially the method used throughout machine learning. So we can also learn another thing from this. So for example, if I tell you that I don't have Gaussian noise, but some other noise distribution, then you might say, okay, I could do a similar derivation, but I might actually end up with a different criteria, a different algorithm. I'm no longer justified to use least squares. Maybe there's something better than least squares if I have non-Gaussian noise. And that's true. So depending on your noise distribution, you can get and will get other least squares estimators that are probably going to perform better than this. But if you trust your noise is Gaussian, then this is a pretty good thing to do. Okay, so that's just an example of applying ML estimation to linear regression. Like I said before, we will see it applied to several other problems in the next unit. Okay, so that's ML estimation. We also said there's an alternative called map estimation. So it's pretty similar in spirit, except you start out instead of so remember in ML, just for reference, in ML, we want to maximize the probability of y given x and beta. We want to maximize that. So now the difference with map is you want to maximize this instead. You want to maximize the probability of beta given your data, y and x. And from a high level perspective, this actually, I think it even makes more intuitive sense than this. These are your known quantities. Seems like we should be conditioning on them. And this is the unknown quantity. And here we're just saying, find the most probable beta vector given this statistical model and the data that I've collected. That makes a lot of sense. There's sort of a catch though. As we'll see, in order to do this, we need a bit more information. And in particular, we need the probability of beta unconditional. And that's something that often we either don't know what it is or we're hesitant to make assumptions. And for that reason, we may not want to do this. But if we have some, pretty good justifiable assumption on the probability of that beta vector, then, this might be the more appropriate thing to use over maximum likelihood. So let's see how this goes. So our first task is to figure out how do I turn this probability of beta given y and x into something a little bit more tractable, into quantities that I have. And so to do this, we're going to use something called Bayes' rule. And to understand Bayes' rule, let me start by just giving you, just reminding you that, for example, if I have two random variables, probability A and B, I could have a density, which is the density of A and B together. There's a couple ways I can write this. I can write this as probability A given B times probability B. I can also write this as the probability B given A times probability of A. So these are just standard ideas of conditional distributions that you might remember from your probability class. And so given that these two things are equal, you can actually see how from here you could get the fact that probability B given A is probability A given B times probability B over probability A. So to get that, I just, I said this equals this. I divided both sides of the equation by this, and you get this. And this thing is called Bayes' rule. Now, the way I explained it here, it was sort of a little bit simpler than how we're going to apply it in the sense that there is no conditioning on here. But you could also extend this, and you could extend it by conditioning all of these on some other variable C. So if I condition on C here, then I add C to my list of conditioning there. I add C here, and so on and so on. And you get a version of Bayes' rule where every probability here is also conditioned on some new random variable. And that's actually the case that we need to use. What we want to do, so what Bayes' rule essentially does at a high level is when you have a conditional distribution like P given A, it allows you to swap the locations of B and A. So here, instead of B given A, we have A given B, and then we have the two margins. So that's what we want to do here. We want to swap these. I want to swap these. And how we do that is we do Bayes' rule. So for Bayes' rule, we're going to have probability of the y vector given the beta vector in the X matrix times probability of the beta vector given the X matrix over probability of the y vector given the X matrix. So again, we're just conditioning on X in all cases. And apart from that, we're just using Bayes' rule. Okay, now there's one more simplification we can make. We can simplify this term. So this is saying, the probability of our prediction coefficients given our features. Now, if I gave you both the features and the targets, you can make sense of those prediction coefficients. But if I give you just one or the other and not both, you can't really say anything more about beta than what you knew originally without any data whatsoever. And so what that means is we can do one final simplification. The first term is the same. The second term, we change to just probability of beta. Okay. And again, okay, that's what we change here. So again, the reason we're able to do this is because if you give me just the features alone without the targets, that doesn't give me any additional information about beta. So I can replace this conditional distribution by just the original, what we call the prior distribution on beta. So the word prior in this case means prior to collecting any data, you may have some belief on those coefficients beta. That's the prior. Okay, so finally, at the end of the day, this is the equation we get for map estimation, although we can actually make one more simplification. And that's that if we're trying to maximize over beta, you can see that this denominator is not really playing any role whatsoever in terms of that maximization. So we can finally just write this as probability y given beta x times probability of beta. And in fact, now when you step back and look at this at a high level, you might recognize that this is actually the likelihood that we use in maximum likelihood. But now we're multiplying that by this prior probability. So in maximum likelihood, it's essentially like saying, you don't have this, like all values of beta are equally probable. But when you do map, you say, no, some values of beta are more probable than others. You make some assumption on that, and then you maximize this product. Okay, so in terms of interpretation, the likelihood describes how well beta agrees with the data, X and Y, and the prior is basically giving us information on how well beta agrees with our prior beliefs about beta. Okay, so this is map. Let's see some examples. Oh, actually, one last thing before we see the examples. So similar to how we did this with maximum likelihood, here we have the product, maximizing the product. But we said that that's equivalent to minimizing the negative log of the product. And finally, when we take the log of this product, we get minus log of the first, minus log of the second. So let's again apply this with the linear Gaussian model that we saw before. In this case, we previously derived that the first term, minus log likelihood, took this form, minus x beta squared plus some constant. And this is a constant with respect to beta. So we derived this a couple pages back. And so if we plug that into our expression above, we have the map beta is the minimizer over beta of this quadratic term. This is a constant with respect to beta, so for this minimization, we ignore it. And finally, we have this last term here, minus log probability of beta, or density of beta. And one final thing we can do is that if I multiply this whole thing by a constant independent of, or invariant to beta, we get the same minimization. So what I'm going to do is I'm going to multiply this by 2 sigma squared, which is going to cancel this, but it's going to put a 2 sigma squared over here. So we get arg min beta of y minus x beta squared minus 2 sigma squared log probability of beta. Okay, and finally, we can step back and realize, oh, this is actually the RSS as a function of beta. This is the thing when we do maximum likelihood, we want to minimize. When we do least squares, that is minimizing it. But now we have this other term, and we recognize this as regularization. This is plus our phi function of beta, our regularizer. And we studied 2 varieties of this, L2 norm-based regularization and L1 norm-based regularization, Ridge and Lasso. So now we can see, we can interpret Ridge and Lasso from the perspective of map estimation for particular choices of this probability beta. So let's figure out what is the probability of beta for Ridge and for map. Okay, so this is what we have from the previous page. So if we have prior belief before we collect any data, that our beta coefficients are independent and identically distributed, they're all distributed as zero mean variance V Gaussian. What does that tell us about the joint density function? Well, because of the independence, this is the product of this Gaussian density for each individual beta. And this is our Gaussian equation for zero mean, variance V. So if I take the log of this, we said the log of the product turns into the sum of the log exponents. So essentially taking the log, we'll get rid of this, and put the sum over j up inside there. And finally, when we do that sum of the squared beta j's, you get this squared Euclidean norm. And then the log of this will give us this constant here, but this is a constant with respect to beta. So this is, this is really the part that is going to influence us up here. So we plugged essentially this into this expression, and this is the expression we get. And we notice that this is exactly ridge regression, but even more, it tells us that the value of alpha that we should be using for ridge regression, if we happen to know the variance sigma squared on the noise in Y, and we happen to know the variance V of the beta coefficients, then it tells us that this is the right value of alpha to use. Now in practice, when we use Ridge, we really don't know these things. We might not know the variance of the error in Y, might not know the variance of the variance of betas. And so we just treat this as a tuning parameter and we use cross-validation to tune it. But if you did know those values, then you wouldn't need to do cross-validation. This should be what you want to use. Okay, so that's what we see. So if our prior belief is Gaussian, we get Ridge. On the other hand, if our prior belief is Laplacian, so the Laplacian distribution, if Gaussian looks like a bell curve, Laplacian is peaked like that. And its equation is actually quite a bit similar to Gaussian, except we take this square and replace it with an absolute value. And instead of like a variance V, you have what's called a scale parameter lambda. And so the form of this is just a little bit different, but again, it ensures that this integrates to 1 for every beta j. So anyway, this is our, let's assume the required belief looks like this. If that's the joint density over the different betas, then when you take the log of this, the log kills the exponential and put this product inside here as a sum. And when you have a sum over those absolute values, that gives us our L1 norm here. This other term shows up as this constant, but it's a constant with respect to beta, so it's not really useful for this minimization problem. So the final step is basically to plug this into this, and you get here, which is lasso with a particular value of alpha. So similar to Ridge, if you happen to really know this based on knowing the distribution of those coefficients, you could just directly set alpha and lasso. But in practice, we tend to not know this. Maybe we don't also know the variance here, and so we can just do cross-validation tuning. Okay, so just sort of a summary to wrap up this stuff. Supervised machine learning can be framed with statistical parameter estimation. To do this, we start with a probabilistic model of our data. We investigated the linear Gaussian case as an example. And then we say maximum likelihood is just maximizing that probability model, or equivalently, minimizing the negative log of that model. On the other hand, ML is an alternative where you maximize something different, the probability of your unknowns given your data, and that is equivalent to minimizing the negative log likelihood plus the negative log prior. So the latter employs this prior belief. And we have to be a bit careful in terms of applying prior belief. So in some cases, we're using this, like in Lasso and Ridge, as a way of helping with correlation or doing feature selection. But in doing so, there's generally some sort of bias variance trade-off. You put in this prior belief. It may bias you a little bit, may shrink your coefficients, but on the other hand, maybe it turns off those coefficients and reduces your variance, and overall it's a win. So it's something you have to choose very carefully, and it's something that's pretty application specific. But Ridge and Lasso are very well known approaches that are pretty well trusted and pretty well used in a lot of different applications. Okay, so that pretty much is the main technical content of this unit 4. The last thing I want to talk about just very briefly, because it relates to something in the lab for this unit, is how we do linear regression with vector value targets. So what I mean by that is until now, we have been focusing on scalar value targets. So in other words, we might have like D different features, but we're using them to predict a single target Y. So this is what we've done until now. That would be scalar value targets. So instead, we might consider vector value targets. So now, this means that instead of just trying to predict a single y. We're actually trying to predict a whole bunch of different y's. And so here this would be like the ith training example of y1 and the ith training example of yk. So from the same features, you're trying to predict multiple things simultaneously. So the extension is really not that complicated. You just, rather than having like, a scalar, you can make a row vector for each sample of your targets. And the way that we handle this is, if on the left side we have a row vector, then on the right side of the expression, we must also have to have a row vector. So here we have our a matrix like this, which actually this is a row, basically a row vector. And then this is a matrix where this beta 1 coefficient vector is in charge of predicting this target. The next beta 2 is in charge of predicting the next target, and so on. And the last column, beta k, is in charge of predicting this. So instead of having a coefficient vector, we actually have a coefficient matrix. And since there's no such thing as capital beta as a Greek letter, we'll just call this capital B. So this matrix is going to be D plus 1. In general, we're going to have our intercept term and our D different features by K, where K is the number of targets we are predicting simultaneously. In the old days, when we started this, you could say that K equals 1, but down here, basically K is greater than 1. Okay, so that's what happens for the ith sample in our training data set. As usual, we stack samples one on top of each other. I is going down this way. And now we have a whole matrix of targets. So this is as we go down in our samples, it goes this way. As we go across our different targets, we go across that way. The A matrix is the same as before. It's just all of our features as we go down the different training examples, appended with the column of ones to handle the intercept term. And now, instead of just having a single beta vector, we have our beta matrix. And inside each one of these vectors, the first element would be the intercept term for the first target. And then you go to the next vector. For that beta 2 vector, the first element would be the intercept term for the target k equals 2 and so on. So this is what you get. And when you step back and just write things in terms of matrices, you have y approximately equal to a b. We're now, instead of y being a column vector and this being a column beta, we have y the whole matrix and b is a whole matrix. So really that's the extension in terms of the model. In terms of what happens with how we do the prediction, we can go through the same maximum likelihood approach. We have a linear Gaussian model of this form, where in this case, what we'll assume is this E matrix is filled with different residual terms, different ones for different samples and for different targets. If we assume that they're all Gaussian, zero mean, sigma squared, we could solve for, let's see, I don't think I have it here. You could solve for the linear regression and you would find that you get this quantity as your negative log likelihood alone. Now in ridge regression, as we know, we also put a prior on the betas, and that will give us this extra term. So I want to emphasize one new thing here, which is this Frobenius norm. So the Frobenius norm is a norm on matrices, and it's basically just the sum over all the elements in the matrix of the squared entries. So in some sense, it looks a lot like the Euclidean norm. It's just that when you have multiple columns, you just add the sum of those squares as well. But the reason why it's important to put a little Frobenius down here is if you write a quantity like this, a matrix with the standard norm, it turns out that the standard norm for matrices is not the Frobenius norm. It's something else called the spectral norm. And it essentially tells you what is the biggest gain that in terms of norm that that matrix can give you when it's used to multiply a vector. That's actually quite a bit different than this. So we have to be a bit careful. We don't want to put a 2 down there. We don't want to leave nothing down there. We really do want to write the Frobenius norm in both of these cases. Okay, so this is what we get for ridge. For lasso, we have this expression. So here we have our RSS, and over here we have our 1 norm. And it turns out that the matrix 1 norm and the vector 1 norm have the same notation. You just put a 1 in the subscript. Like that. Okay, and finally, scikit-learn's linear regression methods. They all work out of the box with vector value targets. You don't need to do anything different. You just need to, give them a matrix of targets, and then it will return for you a matrix of least squares coefficients. So that's it. This is what's used in the lab. But other than that, I think it's pretty straightforward. So that's all we have for this unit. So next time we'll change our task, and we'll learn about classification and start focusing on that for the next few units. All right, so I'll see you guys back in Columbus on Monday. Have a good weekend.